So, continuing our discussion on the specificity, I have to tell you that the unfavorable ratio of the analyte to that of matrix components, as in the case of trace analysis, most of the spectrophotometric procedures are rarely specific. That means, one reagent, one analyte is never possible. Okay. We have to take it granted that there could be a single reagent may react with several parameters if present. It may give a different color or it may give a same color. So, it is unreasonable and unpractical to expect there is a one reagent for one analyte, not at all possible. Okay. So, whenever possible, that means there are no other materials present, then one reagent, one thing is possible. Suppose you want to determine a very pure quantity of very pure zinc, there will not be any other material, so it becomes specific. But in a given matrix, there may be, you do not know, quite often we do not know what all it contains. It is impossible to know everything. So, it may be possible sometimes to know what are the concomitants. In that case, we can take precautions. Okay. Now, I have told you that a substance, a reagent can be made specific for a reagent under optimum conditions, and these things include pH adjustment and addition of complex forming agents. We can use redox reactions or sample pretreatment. Now, coming back to this last sentence, what you are seeing on your screen is the way ahead for us to make a reaction specific. For example, if there are 2 or 3 substances with which the reagent, a given reagent gives colored substances, we can optimize the pH at which it will react with each of the analyte. So, if I plot absorbance versus concentration and pH, I may have forget about concentration, the substance may react with to give maximum absorbance at, let us say, about 4, 5. Another substance, if present, it may also react, but it will give you a maximum reaction product at pH 9. Okay. Now, by operating the reaction at pH 5, I can happily make sure that at pH 9 is not obtained. If I work at pH 5, pH 9 reaction will not occur, or pH 9 if I maintain, pH 5 reaction at pH 9, reaction at pH 5 will not occur. Okay. So, what I do essentially is I conduct a reaction at pH 5 or pH 9, because an element X reacts at pH 5 and element Y reacts at pH 9. So, if I use a buffer of pH 5, I ensure that the reaction pH will not exceed 5. So, Y will not interfere in pH 9. So, we are talking about the pH, that is about the pH. By using a buffer, I make the reaction mixture to remain a perfect pH 5 or pH 4, pH 7, etc. So, the other reactions at different pH will not occur. That is one way of making a reaction specific. Another way is addition of complex forming agents I can add. Suppose there are two substances reacting with the analyte at the same pH. Then what do we do? Two substances reacting at the same pH to give you same colored solutions. Then what I do is I add a complexing reagent. Suppose I have X and Y, I complex Y leaving X in the solution. So, Y will have already been complexed, so it may not react with the reagent with which I am dealing. Sometimes it is possible for me to use redox reactions. I can oxidize one of the components, make it render harmless or not follow the color reactions. I can do a sample pretreatment. Sample pretreatment to eliminate one of the components Y, for example. I want to determine X, I have to eliminate Y. I can do sample pretreatment, and this sample pretreatment takes several forms. For example, take a look at this. It is necessary. I can do the extraction, I can do the physical separation, I can do filtration, and several other things I can do. So, when such separation itself is not possible or pH adjustment is not possible, redox reaction is not possible, and then the complex formation also is not possible, then what happens is it is again we chemists have a different tricks to sort out this problem. So, what are the possibilities? It is often necessary to resort physical separation of itself of the analyte. I take out the analyte from the matrix. I have 1 ton of the ore containing 1 ppm of gold. So, I take out 1 ppm of gold from all of it, leaving remaining 1 ton here, and then I dissolve that 1 ppm and do the necessary analysis. That is known as physical separation. Okay. Now, how do I do the physical separation? There are a lot of tricks we employ. When there are no interfering substances possible present, sometimes it is necessary to separate or concentrate the analyte. For example, if the substance is very dilute, I just evaporate, take 1 liter and evaporate to 5 ml. So, I am concentrating. So, it will, if the diluted substance becomes more concentrated, to bring it into within our measurable spectrophotometric finish. Okay. So, that is one way, and sometimes whenever we do this, we have to define a recovery factor. For example, how much you can recover from a separation procedure. Would it be 100%? No, it will not be 100%. It may be 95%, it may be 90%, it may be 85%. Then if you want to report the correct percentage of the substance, you have to do the correction that you have recovered 85%, but recovery percentage itself is 85. So, the actual substance would be 85 plus 15%, which is not recovered. It may be remain in the original matrix. So, this correction factor becomes very important whenever you are dealing with very low concentrations of the substances. Usually a recovery of 95% is considered satisfactory in all spectrophotometric finish. For example, what we do normally is, whenever I develop a method, spectrophotometric method, I add an analyte. I know how much I have added. From the spectrophotometric method, I carry out the usual blank, this, that, etc., convert it into absorbance, refer it to calibration curve, calculate how much I have, what is the how much is the concentration. So I know what I have taken, I know what is the response calculated. So this difference, it may be 95%, it may be 99%, it may be 90%, etc., because you won't get 100% theoretically at all. So whenever you do that is known as standard addition. I have already referred to the standard addition technique in the spectrophotometry topic when we were discussing instrumentation. So a 90% recovery is considered acceptable. That means it is considered almost 100% accurate when the sample is in the range of 0.0001 to 0.001%. That means 10 ppm, 1 ppm to 10 ppm level. If you get 90% recovery, we consider it as a fairly clean method. There is no problem with the analysis. But suppose you get 50%, then that means it makes lot of difference. We have to think why we are getting only 50% when the satisfactory method is around 90%. So what are the different methods of separation we normally employ? And these include precipitation, co-precipitation, adsorption and related processes. So these things, for example, the general process, what do we do? It involves creation of two phases, one which will concentrate the analyte and the other one which will contain all the remaining matrix. A preformed slightly soluble substance may be used effectively in number of cases to separate a trace constituents. This theoretically, while reading it may look somewhat complicated to you, but what is important is a soluble substance. We just have to dissolve the sample, leaving the other things undissolved. Then you filter it, that is a way of concentration. That is what we mean. A preformed slightly soluble substance may be used effectively in a number of cases to separate a trace constituent. The simplest one is precipitation. So precipitation is not generally used for trace constituents because of difficulties in colloidal formation. For example, what happens is, whenever you are trying to precipitate a very small quantity of the substance, the critical size of the precipitate may not be exceeded to make it visible like a precipitate. In that case, we call it a colloidal solution. It may look colored or it may not look colored, but if the sample, if the analyte is in ppm level, 99% chances are that it will form a, even if you add a precipitating reagent, it will form a colloidal solution. For example, we all know from chemical history, our chemical practice in PUC and college level, that if you take silver nitrate, add sodium chloride, silver chloride will precipitate. But there is a limit to which silver chloride can be precipitated, whatever is the amount of chloride you add. So if it is 1%, definitely you will get a precipitate. If it is 0.1%, you will still get a precipitate. 0.01%, you may get a precipitate. 0.001%, we do not know. The precipitate may be there, but our eye is not sensitive enough to detect a precipitate. Sometimes the precipitate the reagent what we add is in so high concentration that it may form a colloid. So, colloids are not filterable. So, a colloidal formation is normally not possible, not preferred. So, sometimes due to supersaturation, to precipitate I add more substance, and then what happens? There may be a supersaturation, it may redissolve again, then you do not have a problem at all, and sometimes it may lead to filtration problems. Therefore, a small amount of another substance we add with low solubility product, which carries the element of interest also. That means, I am adding another element which precipitates, and along with that precipitate it will catch the analyte which is in very low concentration. So, that is known as carrier or a collector. So, what is a collector? A collector is a substance that is present in large concentration and precipitates. While precipitating, it will carry the analyte also. So, for example, I am showing you this slide that aluminum is a collector for titanium in small quantities. If you want to determine titanium, what we say is add a little bit of aluminum hydroxide will precipitate, and titanium also will precipitate along with that, not as titanium hydroxide, but as titanium oxide, but along with aluminum hydroxide. So, aluminum is a collector and titanium remains is the analyte. Similarly, people have used lead sulphide for molybdenum and titanium and copper, zinc, etc. This kind of collector analysis, collecting analysis is a very common analysis technique in most of the spectrophotometry. Especially these are useful in geological samples. And another well known example is ferric hydroxide, that is used as a collector for arsenic and phosphorus. So, the chemistry of these precipitations and collections is again a subject of special information, special chemistry. Many people are aware of it, but whenever you come across a method normally that requires a collector, the method does make a mention, standard method if you find it from Google or standard methods, AOSE methods, etc. They will make a mention of these techniques. So, one has to be careful. Adsorption is again another process and other related processes are there. Then suppose again another possibility, that is it is not possible to add the collector, you do not find a suitable collector, then what do? Other tricks, we go for other. What is the other trick? That is ion exchange. So, what I do? I just take the sample, put a little bit of ion exchanger, shake it or pass it through a column. So, it can be cationic or it can be anionic resin that can be used to separate the anion from a large volume of the liquid sample or effluent sample. So, it gets adsorbed on the ion exchange column, and then you have to strip it. You have a very small quantity of the substance that is the analyte for spectrophotometric finish. So, ion exchange is a very wonderful technique for concentration of the analyte when precipitation methods fail. Quite often it becomes a preferred method compared to precipitation. So, examples include copper and then chloride, nickel, zinc, etc. These are from distilled water, and plant digest and superphosphate, they are all used as in the routine samples, and all these things can be concentrated using Emberlite IR 100, that is ion exchange resin. Emberlite IR 100 is a cation exchange resin, and there are different categories of ion exchange resins which can be used for different elements, and the such data is also available in the standard textbooks or in the standard methods. Iron by permitite with desorption using sodium chloride is another method. For example, if you have iron in a given sample, then you can use a little bit of permitite, that is a zeolite, with desorption using you can shake it, iron will go along with the permitite, then add a little bit of sodium chloride, sodium will replace iron and iron will come back in a pure form for you to analyze separated from the other matrix elements. So, ion exchange adsorption is again a special technique, very useful as an addendum in for spectrophotometric finish. Now, electrolysis, another technique. What happens is suppose you want to determine copper or zinc, then it is very simple. All you got to do is bring everything in solution, put a copper electrode and then collect all the copper, do the electrolysis, collect the copper and that carry out the analysis. Very simple technique, but very effective, but not many laboratories do have these kind of accessories for specific purpose. Therefore, it is important for us to know the potential and if necessary apply it wherever necessary. So, the examples include copper, lead, mercury, silver, gold, any element that can be coated electrically, that can be precipitated electrically on a cathode, that should be useful to concentration. So, sometimes it may not be possible to determine element as such, sometimes it may precipitate or it may deposit as oxide also. That is also acceptable because oxides can be stripped, dissolved in acids and then with a normal spectrophotometric finish we normally end up having the spectrophotometric finish. Now, another way is precipitate, macro constituents, knowledge of qualitative and quantitative analysis, what you did in high school and maybe first year, second year, third year BSc, gravimetric as well as qualitative analysis tells us different ways of precipitating the whole matrix. For example, you can see in dilute sulfuric acid medium, that is in the college experiments, group 2 chemical analysis says add sulfuric acid, dilute sulfuric acid medium, iron, cobalt, nickel, cobalt, nickel, zinc, chromium, cadmium, all these metals are deposited on mercury. Take a little bit of mercury, add a little bit of sulfuric acid and all these metals will form amalgam, remaining metals will not form the amalgam. You filter it and then you just wash it, take out the amalgam and you have the evaporate the mercury and then you have all the enlight element in a small volume for a regular routine spectrophotometric finish. And sometimes suppose you have in the sample aluminum, titanium etc., they do not form the amalgam. So, if you want to determine amalgam, you should take the aqueous extract, that will concentrate aluminum. If it is copper, if it is chromium, it is the amalgam portion that you have to shake it with acid, remove it from there and do the analysis. If it is aluminum, titanium etc., from the same solution you just filter it, remove the amalgam, the remaining aqueous solution you can determine using the regular spectrophotometric finish. So, another technique, I have to give more emphasis to this technique for you to appreciate because this is something to do with extraction. So, a very very important technique for extraction by an immiscible solvent, very frequently used, ideal method for separation of the analyte from large quantities of foreign substances. The process is very selective. Sometimes you may form a complex, extract the complex in a small 5 ml volume from 100 ml, 200 ml, 1 liter. You take 1 liter in a conical flask, shake it with 5 ml of the substance, everything comes in 5 ml of the organic substance, organic solvent, and you can determine. The process is very selective. There are hundreds and thousands of papers where an analyte can be concentrated using a immiscible solvent. It is also a metallurgical process for the separation of the metals and several other substances, and the beauty is the process can be made very selective because there is a large number of organic solvents which are specific to particular analyte. Sometimes the isolation can even exceed 99.99%. What more do you need? This also helps in concentrating the analysis as well as helps you in analysis. For example, I can give you a couple of very simple examples. Ferric chloride, by ether and ketones. Ferric chloride can be concentrated. You have a large quantity of a substance containing iron, you want to determine how much of iron is there. For example, I can give you a very practical example. For example, most of us know that apple contains quantities of iron. That palak what you eat every day in your regular food, it contains iron. You want to know how much of iron it contains. Now what do? You dissolve the palak or apple in mash it, take an aqueous extract, but then aqueous extract will be 100 ml or 500 ml. So, concentration of iron will be very less. What I do? I take all the 500 ml in a conical flask, add 5 ml of ether. So, all the iron will get extracted into ether as ferric chloride. So, simple technique, wonderful technique actually. So, chloroauric acid, gold, you just have to add hydrochloric acid, it will form a AuCl4 minus, and that can be extracted by ethers and ketones. And chloroacids, a lot of chloroacids, organic substances can be extracted using all these extractants. Similarly, uranium, thorium and ceric nitrates, they can be extracted by carbon tetrachloride, very simple. So, there are actually in more than 50% of the organic analytical procedures for most of the metal ions, they do have a solvent extraction as part of the standard procedure to determine to a spectrophotometric finish. There are two advantages that happen whenever you do solvent extraction. One is the analyte gets concentrated, and the second is sensitivity of determination. That means the detection limit gets reduced. That means you can go down to very low concentrations and more accurately also. A very interesting technique. So, the advantage of this solvent extraction is that the acidity plays a very very important role. The effect of foreign substances on extraction and relativity is very slight. So, it can be pH independent provided pH does not alter much. Synergistic extraction also you can use. So, what is synergistic extraction? If I make a statement that you can use synergistic extraction, you may not understand, but I can, if there are two substances, instead of one extractant you use a second two extractants, then what happens? Both extractants will try to extract the same sample and the extraction efficiency will be more. Sometimes whenever you use two extractants, the combined extraction will be much more than the sum of their individual extraction. You understand? I use X, I get 90%. I use Y, I get 5%. If I use X plus Y, I get, instead of 95%, I get 99%. This is known as synergistic effect. The synergistic effect, I can give you a small analogy, that if you are climbing a hill in a train, they put an engine in the front to pull and they put an engine at the back to push. So, it is something similar. So, one is pulling, another is pushing. So, it is a synergistic effect, and which is more advantageous. So, synergistic extraction also gives you an added extraction efficiency. So, in the next few slides, what I would like to do is describe several features of spectrophotometry which can be used to assess the usefulness of the method. Again, it permits the comparison of colorimetric methods of the same analyte, because this brings me back to the starting of this today's class. That is, I had explained to you that there are more than 100 methods maybe for one or two analyte. Then how do you compare which is the one which is the ideal one? So, in the next class, what we will do is we will continue our discussion about these aspects, comparison and specific characteristics of spectrophotometry, and then we will go on to study the individual parameters. So, thank you very much. Have a nice day.